And let's start. And today we're happy to have Yanki Lekili from the Imperial College, and first time very unusual format which he proposed and even insisted. And the title of his talk is Equivariant Fukaya Categories at Singular Values. Yanki, please.
Okay, thank you very much. So I see some familiar names. Hi, I haven't seen you for a while. So thank you very much for the invitation, Jan. And today I will talk about a joint work with Ed Segal. It is a kind of ongoing project, so not everything is finalized. But and also I should make the disclaimer that there is not really a theorem in this talk. It's more about some conjectures and some examples.
Fukaya sometimes used the word theorem for something which proof is not quite finished, but you have a sketch, probably. You will have theorems.
Right. So the idea here is in this talk is not about there is some problem with the technicalities. It's more that we discovered some new framework, and there's a lot of conjectures that came out of it, and we just didn't have time to write them, but we are still excited to talk about it, so that's what I'm doing. And anytime, please feel free to interrupt. So I will first recall equivariant cohomology. So this is a contravariant functor from manifolds to graded vector spaces. And it satisfies three important properties. So the first one is if the action is free, you can take a quotient of the manifold, and then you can take the usual cohomology. If there is an equivariant map inducing homotopy equivalence, then we get an isomorphism. And finally, there is a Meyer-Vietoris kind of property. If you have equivariant invariant open sets, then you have a long exact sequence. And in fact, these properties essentially characterize equivariant cohomology, so you don't have to know more than this if you have never seen it. And so one important computation is the equivariant cohomology of a point. So equivariant cohomology of a point is the polynomial ring with, but it's the graded polynomial ring with the degree of the variable in degree 2. So how to see this? Well, one way to see is to consider the infinite sphere, and with its S1 action, just coordinates-wise S1 action, and it's well known that infinite sphere is attractable. So we can, in fact, it's very easy to prove. If you take an algebraic topology class, you probably have seen it, and then you can quotient this infinite sphere and get an infinite projective space, and the cohomology of that is precisely this ring. And the importance of this ring is that the equivariant cohomology is in fact a module over this ring, because every manifold maps to a point in an x1 equivariant way. Okay, so the two-sphere is where I'm gonna give an example. So we can cover the two-sphere with these open sets, so complement of the North Pole and South Pole, say, and then the S1 action that I have in mind is the standard one that fixes this 0 and infinity. Okay, so how do we compute this S1 equivariant cohomology? Well, we can apply the Meyer-Vietoris sequence, as I said, to this open sets, and then we will see that it kind of splits, and so the degree 0 part is like this, and then these are for I greater or equal to 2. It's just a direct sum of the S1 equivariant cohomologies of U and V. So from this you can compute that the S1 equivariant cohomology of the sphere is just this ring. So basically, the Cx side is the S1 equivariant cohomology of a point associated to U. So U is contractible to a point equivariant way, and similarly V is contractible to a point. So that's the Y variable, but there's a common cylinder where they overlap, and that gives us that the unit is the same in each side, and we get this ring. Okay, so there's no one who turned on their videos or anything, so I don't know if I'm still online. So
yeah, you're still online.
Okay, and people are following, right? Okay.
Well, it's much more difficult question, so I cannot answer.
Okay, so please feel free to keep your videos on, and then that will be some feedback, at least to me. Anyway, so this is the problem with online talks. Anyway, so this is a classical computation that you can do, and it's fun. So it's this ring. Okay. So, and moreover, as I said, it's the action of equivariant cohomology of a point is given by, in this case, given by the t equals to x plus y. So t acts by multiplication by x plus y. Okay. Right. So also, sorry, one more interruption. If you have any questions but you feel shy about saying it with voice, you can write it in the chat, so I can see the chat and I can answer when I see it. Okay. So next, well, we covered some topology, but now we want to do symplectic topology. So we will study Hamiltonian S1 actions. Okay. And to upgrade topology to symplectic topology, the obvious way to do is to take cotangent bundles. So we will consider cotangent bundle of S2. Okay, so this is an exact symplectic manifold, and so I present it as given by this equation in affine space, and that induces that also induces a symplectic structure that's exact, and then it has an Hamiltonian S1 action, which is rotating the x and y coordinates in this presentation, and the subject of this talk, the main subject, is the S1 equivariant wrapped Fukaya category. Okay, so this we'll get used to it slowly, but so people are more or less familiar, I assume, with some Fukaya categories, and this is a symplectic manifold. S2 is a Lagrangian submanifold here, and then there is a way to do Floer theory in an S1 equivariant way.
So do you consider fully wrapped? I mean, let's forget about the S1 action, which is the main topic probably for you, but if we forget about it, so are we talking about fully wrapped, or you will consider partially wrapped, which is one at least?
I am flexible about those choices at the moment, so I can do any of them. So, but let's consider, as it's written here, it's the fully wrapped category, but I want to study the S1 equivariant version. So when it's a partially wrapped category, one usually puts a stop in the notation, like a relative to some stop like this. So, but I didn't do that here. Okay, so the simplest way to approach this is first to consider a compact exact Lagrangian. So when I have a compact exact Lagrangian, such as S2, in this example, the zero section, so it's the zero section, it doesn't bound any holomorphic disks. So therefore, in some sense, the Floer theory is not that interesting. It's just the usual topological, singular cohomology. And so that gives us a way in before we do more fancy stuff.
So Yanki, I'm a bit confused. The left-hand side, should we know what is equivariant Floer, or we should guess?
this is equivariant S1 equivariant Floer cohomology of this Lagrangian. So I mean, it's defined in the literature, so there are some papers on it, but I'm not going through its definition. I'm just giving you as a fact that when it's an exact compact Lagrangian, it agrees with the usual S1 equivariant cohomology. So this is analogous to the statement in the non-equivariant world. So when you have an exact Lagrangian, it doesn't bound any holomorphic disks. Therefore, the usual cohomology does not get deformed. So, and this is the same here. Okay, and so we can compute this Floer cohomology, and it is because we did the classical computation, it's the same ring. So, okay, so the picture that we have, here's a picture. So this is the base we are projecting to this z coordinate, and the fibers are conics generally, and there are two singular fibers, which are these conics, and the S1 action is rotating these fibers, these conics, in the obvious way, and the sphere is somehow this matching sphere here. So that's how the picture of this cotangent bundle of S2 is. And we just I just told you what the S1 equivariant Floer cohomology of this one is. So it lives over this arc lambda, and this is the base C. Okay. Next, here is a key observation. The key observation that we have here is the following. So this arc that I drew here. Now I will view this arc as a non-compact Lagrangian in a punctured C. So I will puncture these points and then view that as a symplectic manifold, and this lambda is a Lagrangian that goes from this end to this end, so between those ends. And now, so that's called a pair of pants. So it's the complement of 1 and -1 in C. And now we will compute wrapped Floer homology of that Lagrangian. And this is not S1 equivariant. This is a usual wrapped Floer homology, fully wrapped Floer homology. So that's easy computation. There are basically two places where it wraps, and each of them can wrap infinitely many times, and this will contribute powers of x, and this will contribute powers of y. And as a result, in fact, we get exactly the same ring. Okay, so this talk is about why these two rings coincide. Okay, so have I got that across? So there's one is S1 equivariant cohomology or Floer cohomology of this compact Lagrangian that lives in the total space of this vibration, and the other one is the wrapped Floer homology of this base Lagrangian where this S projects to. But there's a significant modification, which is that we don't take the projection of all S, we remove the points where this is singular, and then we project that cylinder. Okay.
So let me just, because I was distracted. So you consider compact base. You do not consider, for example, the fiber as Mohammed does for cotangent bundles to the
right. So currently I'm giving the example of a compact Lagrangian. We can also do the cotangent fiber. We might get into that if we have time.
But this cotangent fiber has to be over the fixed points of S1 action on the base. Yeah.
For the equivariant. So for the equivariant, for it to be fixed by S1, yeah, it must be here.
Yeah. And this projection to C, this C is what? Part of CP1, or I missed it?
Sorry, C is exhibiting this manifold as a conic fibration. So
okay, you need this presentation. Okay.
The equation is xy plus z squared equals to 1, and we are projecting to z. Okay.
Okay.
And then the action is along the fibers. So the action is rotating the fibers.
Okay, so basically you need this conic bundle presentation with this one action.
That's right. That's right. Okay. So we have this, but the claim that we are making that there's an agreement. The agreement is about, on one side, about equivariant cohomology of a compact Lagrangian. On the other side, it's the wrapped Floer homology of a non-compact Lagrangian on the base. And we modify this base a little bit by puncturing the C at the singular points. Okay. So this was one example of a Lagrangian, how that goes. And in fact, our claim is that these categories are equivalent. So on one side, the S1 recurrent cohomology, wrapped category of T star S2, and on the other side, wrapped category of pair of pants. So one nice thing about this claim is if you don't like S1 equivariance, you can actually work with this usual wrapped categories. But you have to take this lower dimensional manifold and adjust it accordingly. So, okay, so now the main part of this talk is to formulate extensions of what's the certain grading structure on P. Oh yeah, so that's I can answer. Hi, Gabe. So this is a pair of pants, right? So and symplectic manifolds, which are not simply connected, they admit many grading structures. But this grading structure for a pair of pants, so for any symplectic manifolds, the possible grading structures are H1 torsors. So it's you can modify the grading by acting with the H1 of the manifold. So usually people take the grading structure on a pair of pants where the winding number around two of the ends is 0 and then the other one is 2. So, but here we have to take the winding number around these ends as plus 2, and then the winding number around the other one is minus 2. So this is the grading structure that extends to C. Okay, so that's the condition that I need. I want the grading to extend, and in the T star S2 case, I didn't have a choice. It's a simply connected manifold. But when I went to this base, I have to explain which grading I'm taking, and there is a unique one that makes this into a graded ring that works for this equivalence. Okay. All right. So what's the general conjecture? So that was a key example that helped us figure out what the general conjecture is. So we take I'll extend this in stages. So let's take the first level of complication. So we will take Y to be a Cn or C star to the n or a general open symplectic manifold, and I'll take an F which is 0 as the regular value, and I will consider a conic fibration over this Y, which degenerates along the 0 fiber of this F. So there is a smooth D. So in the previous example, this D was just 2 points. So don't get too excited in that case. But in general, this will be a hypersurface, and for now we just require it to be smooth. And we take a conic fibration, which is degenerate along that hypersurface. Okay, so that's a symplectic manifold. That's a good symplectic manifold to study S1 actions. So we have an Hamiltonian S1 action just like before, where we rotate the fibers. Okay, and then the first claim is the conjecture A is that the S1 equivariant wrapped category of this X is equivalent to the wrapped category of the complement of this D in Y. Okay, so this is the main conjecture in this case. Is it clear? Any questions?
Yeah, I'm trying to understand it. So for me, the main example will be if I take probably the open curve, open Riemann surface, like Riemann surface minus finitely many points, and look for a conic bundle associated with a spectral curve in the cotangent bundle to the curve. So then X will be 3 Calabi-Yau, and I'm just wondering, so this W, which of course doesn't have any S1 action, it's just Riemann surface probably minus these removed points.
That's right.
And so then I would imagine that there is a basis in the properly defined wrapped Fukaya consisting of spectral networks which are stable objects. Okay, and
on here.
Yeah, on the right hand side.
Yeah.
And I'm just wondering to guess what it corresponds to this total space, to this 3 Calabi-Yau non-compact.
So wait, why is it 3 Calabi-Yau? So in this case, we are talking about the conic bundle. So
I choose in the cotangent bundle to probably to your Y. I'm confused with the notation. Anyway, Y for me is a Riemann surface. Yeah.
Right, and in that case, X should be a two-dimensional thing. So it's
you consider okay, yeah, okay. You consider, yeah. Okay, yeah, I'm mistaken. Yes, so probably I should consider. I should consider cotangent bundle to some auxiliary Riemann surface, and that will be my Y. And then ramification divisor will be the curve in the cotangent bundle, and so then X will be indeed 3 Calabi-Yau. Then W, Y minus D, no, I'm not sure that I cannot say what is it.
Okay. But for now, let's continue, okay? Mm-hmm. So this was a S1 action. It's easy to extend this to a more general Tn action, which I kind of explain here. So then X will be higher dimensional, but still these are simple examples, to be honest, because here it's iterated conic bundles. Okay, so these are kind of examples that come up in mirror symmetry for toric varieties, for example. And then in that case, the conjecture says that the R-dimensional torus acts on the UI VI variables in the obvious way, and then we expect a quasi-equivalence of these categories. Okay.
Yanki, how should I understand the left-hand side? You said that it's in the literature, I believe, but probably that's not something which on the top of my head. So how to understand this equivariant? Roughly.
So far I haven't discussed the definition, and in fact the wrapping is not the main point here. The main point is the equivariance. And the equivariance,
yes, equivariance.
And equivariance, there are many approaches. One of them is kind of the Borel construction. So one can generalize the Borel construction, and then do Floer theory adapted to that construction. But for now, I want you to think about this as let's take exact Lagrangians in here, and then let's view them as just usual singular cohomology of those, but equivariant singular cohomology.
Okay. All right. Okay. Yeah.
All right. So. But there's a surprising thing that's happening here, which is what I want to explain. So it is if I take this preimage of this divisor that I'm removing from Y, right? Then, so this divisor is where the fibers become singular, right? So if I remove this divisor from X, then this is just a trivial, well, not necessarily trivial, it's a principal bundle over the base. And then it's not so surprising that this is true. So if the action is free everywhere, then one expects this equivalence. In fact, one way to see it is sorry. Well, I'll explain a bit more about why one should expect this. But in fact, a version of that was claimed by Fukaya before. So this is just the analog of the fact in singular cohomology we saw that if the S1 action is free, then the S1 equivariant cohomology just becomes usual cohomology of the quotient. Okay, so but what we are claiming is not this equivalence. This equivalence holds true. We are claiming something a bit more interesting. We are claiming that the T equivariant wrapped category of X is actually equivalent to this. So in other words, the deformation coming from putting this this complicated part of the vibration back is actually trivial. So usually when you add divisors to the A side, then your holomorphic curves are allowed to pass through that divisor, and that gives you interesting deformations. In this case, our claim is that this deformation is trivial. Okay, so I will explain a context where this comes from. And for that, let's review Seidel's invertible elements. So one of the earliest paper of Seidel is when you have an Hamiltonian S1 action on a manifold, he constructed an invertible element in the Hochschild cohomology. Okay, so this invertible element can be understood as a natural automorphism of the identity functor, and so it acts on the category, but it actually fixes each object, and it's just an automorphism of the identity functor. So on the homomorphisms of L to L, there is an interesting image of this S. Okay, so this is a categorical way of understanding what Hamiltonian S1 action gives. Okay, so the category that we studied, we claimed we are working with is the category, more precisely, the category whose Seidel consisting of Lagrangians, whose Seidel elements are 1. Okay, so this action is it's the invariant category, and more generally, one can study Lagrangians with this Seidel element, so a multiple of identity. So and these we'll call it as the Lambda components, and in fact these were kind of pointed out by Telemann in his ICM paper, and he called them spectral components of the equivariant category. So some examples to keep in mind are, so if you have a Lagrangian which is S1 invariant and it's monotone or exact, say, and so those give the elements of the invariant category that I was interested in. So for example, S2 was an example of this. You can equip these guys with non-trivial local systems if you can, and then those will give you some elements in these spectral components. And of course, that's one way to construct elements here. In general, when you have an invariant Lagrangian, you can compute this Seidel element and then see which spectral component do you fall into. So, and those have a relation to Hamiltonian reduction or symplectic reduction. So when I have an S1 action, I can construct a symplectic reduction of the symplectic manifold at various values of the moment map. And then we have this Lagrangian correspondence between X and this the symplectic reduction, and this induces a functor between the various Fukaya categories. So whenever you have a Lagrangian correspondence, there is a Kult formalism that induces functors between these categories. And moreover, it's S1 invariant, obviously, this gamma. So this gamma is the image of the moment map, essentially. It's an S1 invariant Lagrangian, so that it actually induces a functor on the equivariant category. And then one expects that this equivariant category, this functor induces this equivalence between wrapped category of the spectral component versus the symplectic reduction. So it's somehow relating the wrapped categories. Well, you have to take S1 equivalent wrapped category of the original manifold versus the wrapped category of the symplectic reduction. So of course this is assuming a lot of things. So one of them is that the alpha is a regular value. Okay, so that you can actually make sense of this as a symplectic manifold. So this is alpha is a regular value, and in fact you should assume that S1 acts freely on the preimage of the moment map, and then you can do the symplectic reduction and consider that wrapped category. Alternatively, you can the claim is that that's isomorphic to these equivariant categories upstairs with the corresponding spectral component.
Does it depend on the regular value?
Yes. Each of them, depends on this alpha. Right. So the alpha here is the regular value where you do this. This is the manifold that depends on where you take the symplectic reduction, and this alpha translates to the value of the sidal element that you have to use to construct to distinguish the spectral component. So each side has the same value essentially, but it's important to note that the left-hand side we can do for any value. It doesn't have to be regular value. It's in an equivariant category. So X itself is a smooth symplectic manifold, and we can do equivariant Fukaya categories of those. But the right-hand side only makes sense at this moment in time for smooth symplectic manifolds. So therefore, we have to take a regular value. Okay. And more generally, so this is an alpha. I took it as a real value, but you can take a complex value as well if you want, and then that corresponds to a B field. So that's a detail. And I should say this kind of equivalence actually is announced by Fukaya at the Miami conference I was at. So he did consider precisely this correspondence to give this functor, and then he claimed that functor induces an isomorphism equivalence of categories. So I want to get back to our example with this in mind. So T star S2 is this nice manifold. The moment map is familiar, and then we look at the regular value, and what we see is that regular value is precisely when alpha is not zero, and then if you take a non-zero alpha, then the symplectic reduction at that value is precisely C. So it's the base that we were seeing, and obviously the wrapped category of C is zero. So C is a subcritical manifold, and so the spectral components should be zero for lambda not equal to 1, right? Alpha translates to e to the alpha, remember? But our main point here is not about these regular values, but about singular value. So alpha equals to 0 is where the interesting stuff is happening, right? So the singular value is where the zero section is. So mu inverse of 0 is where this zero section lies, and we were studying that one, and we can't do symplectic reduction there because it's a singular moment map, it's a singular value of the moment map. The solution that we offer is is, well, just remove the singular part and do a reduction after that. So that gives us this pair of pants that I was talking about. And the wrap category of, so what is written here is a bit confusing. I should have one, sorry, this 0 is not correct. So this should be plus or minus 1. So there is 2 points that we remove, right? Those are the, remember, those are the singular points of the vibration. And we remove them, then we have a reasonable fiber on which we can do S1, we can quotient by S1. And what we get is a pair of pants. And the claim is that the wrap category of that pair of pants is actually recovering this missing spectral component, the interesting spectral component, in other words, right? Because in this example, all the other ones are trivial categories. Just this one is interesting. But this one lies on the regular value, singular value. So this is the singular, again, this B field detail, maybe I'll skip that. All right, so the modified way of saying this, that includes all singular values as well. So in fact, Telemann says in his ICM paper that he doesn't know how to do the singular ones. But this is because you can't do reduction. But interestingly, there's an easy fix. You just have to remove the fixed points. So consider this open part and then divide by S1, the smooth locus. You take the smooth locus, and then the claim is that the equivalence goes through. And
yeah, I'm confused with the notation. I forgot it. Beta in the right-hand side means what?
So beta is, I think it's an unnecessary detail that I put in this slide. So that's the B field.
Field. Okay.
So if you reduce, if you want to study the non-real spectral components, so the real part alpha corresponds to the value of the moment map, but beta corresponds to B field. So. Okay, so that's our main observation that we expect to be true. This is conjecture B. It's essentially equivalent to the conjecture A. The point is that there is a relation to this Telemann's conjectures about the regular values of moment map. So this explains what you should put as a substitute, as a geometric substitute for the singular values of the moment map. Okay.
Hi, Yanki. Can I ask one question? This is Peng. Sorry, I can't turn on my video. It's something wrong with my computer.
Yeah. Hi.
Yeah, sure. So it's great. Yeah, we with Mina, Vivek, and Michael McBrien, we had a similar observation, but we didn't generalize to your general setting. We were considering some hypertoric versus toric, some hyperplane complement in the base, and upstairs we had some hypertoric variety. But the question I want to ask is about the conjecture B, where we don't know any example where the S1 acts on some higher dimensional thing. For example, you consider S1 acting on T star C2, suppose you put some skeleton like the zero section of C2, and you rotate the C2 just by say a 1-1 action, and then our formulation is like you have a reduction of a skeleton. You remove the fixed point to of the S1 action to blow it up, just like what you were doing. Replace the fixed point by a circle or replace something. But in that case, we don't know how to do this higher dimensional case. I wonder, do you have any example where X is not just say complex two-dimensional?
Yeah. All of these are any dimension is fine. There is no restriction in this dimension here. Yeah, you
Yeah,
can just
for example, if your fixed point is a lower
like this
dimension.
one. No, the fixed locus is a codimension too. Is that what you're asking?
Right. What if your fixed locus is lower dimensional?
I don't know that one. It's a codimension 2 fixed locus. It's a hypersurface.
Right. So I guess the question is that is this still true if your fixed locus is lower dimensional?
This I don't know because it doesn't fit into the framework that I studied. So this I don't know.
Okay. Sure. Thanks.
Okay. So, let's continue then. So this was conjecture B. And then I was a little bit careful here. I said I put a vague hypothesis here because in general, I don't expect it to be true like this. You might get some corrections by this associated quantum Kirwan map. But that's again a detail that I can discuss later. So one thing that I want to say now is, so there's these conjectures, and most of the computations we did that helped us arrive at the right statements is via mirror symmetry. And so we did quite a number of computations where the conjecture has a meaning on the mirror side, and then we can compute both sides on the mirror, and then it works. So that's why I want to explain what mirror symmetry says about these conjectures and how it helps. So given a Hamiltonian action on S1 action on X, we have a sidal element as I described, and it makes the wrapped category linear over this. This lies in the center of Hochschild Comology, and suppose you have a mirror algebraic variety to X, then you can say that you can see this S as a function on your mirror variety X check, because zeroth Hochschild Comology of the variety, as we know, is given by functions on that variety. So this invertible element can be viewed as a function on the mirror variety. So S1 action on the symplectic side turns into an invertible function, so a non-vanishing function on the mirror. And then we can soup this up a little bit. So it's rare to have a mirror which is an algebraic variety. You often have to deal with Landau-Ginzburg models, but that's fine. There is no problem with that. So X has a mirror X check, which the W check, and there is an additional function which is this in non-vanishing function. So and what happens to these spectral components? Well, the spectral components corresponds to the values of this function. So basically, the S1 equivalent wrapped category with lambda. These are where sidal element was lambda times identity. Those should correspond to the matrix factorizations of the hypersurface Z lambda, which is the preimage of lambda by this sigma. Sigma is this non-vanishing function that's mirror to the sidal element, and we should just restrict our Landau-Ginzburg superpotential to this hypersurface. And so this is what is the mirror of the S1 equivalent component and at the spectral value lambda. So this is pretty much explained by Telemann, this conjecture, and so we use this as a way to check our original statement. And but there is a little bit of trickery here. So namely, it's not enough. So when you say it's mirror, X is mirror to this, it's not enough to just say these categories are equivalent. It's more data than that, because we want the S1 actions, the equivariant structures on these categories coming from the S1 action should match as well. And the proper formulation of that hypothesis is pretty complicated. And so in some sense, you can take this as a definition of what it means to be. So in some sense, this is a vague and empty conjecture. But on the other hand, this is what we expect if we have a mirror to X. We should figure out this function on the mirror, and then we should compute these categories and try to check our conjecture. So I will make one example here. It's a simple example, but it displays most of the content. So we take X as a local Biot variety, which is the C2 minus a conic. So this is a famous example for which mirror symmetry is very well studied in many ways. So its mirror is the same space, but viewed as an algebraic variety. So the wrapped category of this one is known to be equal to dB_co of this one. But now let's equip this left-hand side with an S1 action. So it is e to the I theta z w in this way. It's again we can view this as a conic vibration, and it's acting on the fibers of the vibration. So on the other hand, one can compute what the mirror to the sidal element is for this one, and it corresponds to this non-vanishing function 1 minus z check w check. So the reason that this is non-vanishing is essentially by definition, right? So we took C2, we projected into C, and where it vanishes is removed here, right? So this is a function that maps to C star, and it is a unique critical fiber when this is 1, right? And otherwise, the fibers are smooth, the C stars. So our claim was the spectral components of the S1 recurrent category should correspond to the fibers of the sigma. So the fibers are C star, so this should correspond to dB of C star. Okay? And moreover, when lambda is equal to 0, the fiber is not C star; it's a singular conic, and the zeroth spectral component should correspond to that singular conic. Okay, so that's a claim how the mirror symmetry should work for these. On the other hand, we can check this with respect to symplectic reduction, right? So the equivariant categories are used as a kind of a middle category that to pass from the B side to the symplectic reduction. So what are the symplectic reductions? Well, if your alpha, so where you're doing the symplectic reduction, is not the 0 value, it's the smooth value, then again it's a regular value, and then you can do the symplectic reduction and you get C star. On the other hand, if you're in the singular value, now it's not you can't do symplectic reduction as before, but we have a modification, right? So we just remove the singularity and then do the symplectic reduction. What we get is a pair of pants. So the claim is that this wrapped category of this pair of pants should be mirrored to the derived category of the singular conic, and that's a well-known example, because these are one-dimensional. Everything is known about mirror symmetry, but that's a very nice confirmation of various conjectures holding together. Okay, so now next last so next direction is I want to talk about non-equivariant categories. So okay, so this S1 equivariant categories where we found a nice meaning for them, both in regular and singular values. They correspond to various symplectic reductions with modifications, but mostly you might care about the wrapped category of X, right? So this S1 equivariant category is a bit more, in some sense, it's a simpler thing than X, right? So it's about the quotient, but maybe you want to recover X, and that's where the CT linear structure comes in. So these S1 equivariant categories have CT linear structure, and in the beginning I told you the S1 equivariant homology of sphere was Cxy modulo xy, and then the T was x plus y. So if you set T equals to 0, then you get the non-equivariant category. So this is again a feature that we have at the level of wrapped categories. So since this category is CT linear, we can take its fiber at T equals to 0, and what we get is the ordinary wrapped category. So the objects, remember, the objects are always Lagrangians in X, but the ones that we were studying here were Lagrangians that were invariant and with properties for the side element. And when we take the T equals to 0 fiber of this category, what we get is the same objects, but now their home spaces are computed in the ambient category. So at least this allows us to recover from this category with its CT linear structure. It allows us to recover some part of this the higher dimensional thing, right? So the game here is following this category. We can reduce it into lower dimensional symplectic manifolds. This is equivalent to the lower dimensional wrapped categories of lower dimensional symplectic manifolds by symplectic reduction. But this that category has a CT linear structure, and if you take T equals to 0 fiber of that CT linear structure, then you actually compute the higher dimensional thing. So you compute some home spaces in this higher dimensional thing, namely the home spaces that are given by invariant Lagrangians. Sometimes those Lagrangians are enough to generate this category, like in T star S2 example. And then you're done. You can compute a wrapped category of that higher dimensional space while just studying wrapped categories of lower dimensional manifolds. So that's the main attraction for us of this framework. Okay. Okay. So in order to back that up, I have to tell you one more thing, which is this category is an S1 equivariant category. It has a CT linear action. And I claim that this is isomorphic to this lower dimensional wrapped category of this lower dimensional one. But in order to take this T equals to 0 fiber, I have to tell you this CT linear structure on the right-hand side too, right? So the right-hand side a priori is not an S1 equivariant category, or it doesn't have a CT linear structure. So of course, by this isomorphism, it gets one. But in fact, there is a natural way to view that as a CT linear category as well. So this extra structure comes from viewing this open symplectic manifold as a complement of a divisor. The divisor itself has what's called the Borman-Sheridan class. So it's an element in the symplectic homology of this open symplectic manifold that's associated to Reb orbits going around the divisor exactly once. So that class gives us an element of the Hochschild homology of this wrapped category, which is symplectic homology, as we know, and that makes this category a CT linear category. So this equivalence more strongly, the stronger claim is that the CT linear structure on the left-hand side coming from the equivariance goes to C tau linear structure coming from the Borman-Sheridan class. And that's vital in order to compute the wrapped category of the ambient category X, the non-equivariant category. Okay, so that's conjecture D. Okay, we are coming to the end, and then I have one more conjecture. So as I said, this is all about conjectures and some new framework. I don't have any theorems to report, but there are many examples that we computed with that backs these claims, and then we are writing a paper displaying those. So the next one is the following. So both of these categories are have this class tau or T, which is in HH2. So that's a deformation class, right? So you can't resist to, when you see a deformation class, you can't resist to deform, right? So you try to deform it. And in fact, there's a geometric deformation in each side. And in the base space Y, this is called the relative wrapped Fukaya category. So this is a category which is, so if you deform using the Borman-Sheridan class of the complement, you get this relative category, and it's a category over this power series ring. It's a formal deformation, and now when you deform the deformation parameter has degree 0. The fiber at 0 is the open thing, right? So that's the Lagrangians that do not go to D. But now I can also do this on the total space X, right? So because we claim that this category is equal to the S1 equivariant category, so that has a CT linear structure, and that's a deformation. And the claim is that the deformation corresponding to the relative category corresponds to the formal completion of this category at the sidal element 1. Okay, so it is a kind of very obvious conjecture, because at S equals to 1, we said that matches with this open one, right? So the spectral component of this at S equals to 1 matches the open one, and now we are deforming in a formal neighborhood of it. And the nice thing is that has a geometric meaning, which is this relative category. There is also, you can also talk about that in terms of the mirror. In the mirror, this S1 action corresponds to sigma, which is this non-vanishing function, right? And the relative category now, so remember the complement was corresponding to this divisor at the spectral, so the complement at lambda equals to 1 corresponds to this divisor, z equals to 1. And now if we deform it, then we will get the formal scheme obtained by completing this. So this should be 1, actually, sorry. We can do it for any lambda, and then it would be, it would be the formal completion at lambda. Okay, so that's basically the end. And here's kind of a summary. We have a conic vibration, singular fibers along a smooth divisor. So we can extend this to T equivariant ones. So it doesn't have to be just S1 equivariant. So, and then the mirror gets a non-vanishing function. So if you had a Tn action, then you would have n non-vanishing functions. So it's an obvious generalization. And then we have these wonderful categories that fit into this kind of diagram with various functions, and basically, and the kind of, I think the original claim that we have, is this equivalence. I think this is at least this I haven't read anywhere. So this is this equivalence that turns this S1 equivariant, the singular category. Well, sorry, the S1 equivariant wrapped category at the singular value has this geometric meaning in terms of the base, which is this complement of the divisor. And that's it. Thank you very much.
Thank you. Thank you for the interesting talk. So, questions? Yeah, by the way, it's question about combining these singular values with with regular values. So, do you have a perverse Schober over these alphas, or I forgot, or e in the power alpha? I forgot your notation.
Right. So let me think about that. So is it a perverse Schober? But I mean, so perverse Schober should be like a locally constant category, right?
Well, it's locally constant, but not constant. In your case, yeah, you said that your fiber heavily depends on alpha. Even if you move a little bit to a different alpha, then the categories are not equivalent.
Right. So here the topological S, there's a topological S1 action on the category, and then we take various different quotients, right? So various different fibers. So it's not gonna. I mean, for example, on the B side, one way to think about it is you just have a fibration from X check to C star. So you just have a map from X check to C star, and you are taking dB co of the fibers, right?
That's fine.
So if that's fine, and you get perverse Schober that way, then
yeah, actually that's what I have in mind, because it's, you know, like in Landau-Ginzburg, when you take different values of the potential, so you can think of them as a family of Fukayas, which form perverse Schober outside of the critical values of the potential. So it looks,
I mean, that somehow that story is somehow in some sense it was understood by Telemann, and like when you do this regular reduction in regular values, the contribution here is about the singular value. So the singular value a priori looks kind of nasty, right? Because the fiber at that point you can't do symplectic reduction. But at least in the setting that I was talking about, in this conic vibration setting, we have a very nice replacement. We just remove the singular fibers, and then we take the wrapped category of that, the complement of the critical locus. So that kind of fits onto that point where it was singular.
Yeah, I somehow think in terms of, you know, like if you decategorify, I'm thinking in terms of the Chekhov vanishing cycles, which probably, I don't know, at the level of periodic cyclic homology of your category. Yeah, not at the level of Hochschild. Yeah, probably at the level of periodic cycle. So then it's sort of, you know, if you believe that you have a perverse Schober, which I don't know, then probably whatever you constructed is an explicit answer for the categorification for the Chekhov vanishing cycles. Yeah, so it's interesting, yeah. And is there always behind some C star action, your S1 is embedded in some, because your examples, they tend to be complex varieties.
That's because the way we studied these examples are, this question was why mirror symmetry. So these examples where mirror symmetry is understood, so we pass to the mirror and then study what makes sense. So it's in general, there is no reason to have C star action. So one can study this question. But as I said, it's also a work in progress. So I don't know exactly what the boundaries of these are, you know. So it's kind of a new thing for me to think about. Yeah.
Okay, thank you. More questions?
Hi, can I ask one more question about the B field you were mentioning? It's like some interesting generalization. Can you say something about this basic example, say like the pair of pants or just?
Well, in the pair of pants, there is no B field. Yeah, B field has to be H.
There is no H2.
Yeah, H2. You need an H2 for B field.
So for the T star S2.
So what happens is the the spectral components where lambda is not equal to 1 vanishes for T star S2. So it's the only thing interesting is at 1, and that's that's where the S2 and the cotangent fiber and so on lie. Yeah.
Okay. And you said this is like a Fukaya announced something like this in Miami conference. Which year was that?
No, it was he only studied first of all he only studied regular values, right? So where
I see.
So the regular value is kind of it's interesting in other contexts, but not in these examples. Most of the time, regular value is very simple. So the interest here is the singular values, and then that's there is no work of Fukaya in that. In fact, I explained him to this, and he was happy to see it.
Right. And so as I was mentioning, we're also reading a paper which has some overlap with your idea, but we basically take your basic observation and in this S1 on this thing, and we just power it up to the usual toric thing, Cox reduction. So on downstairs on the Y mod D, we get some complement of hyperplane. So there we found this skeleton is really useful in the sense that it allows you to do very efficient computation for the upstairs and downstairs categories. So I was wondering,
skeleton where? In X or Y?
In both, actually. Like, for example, in the T star S2 example, your skeleton was S2 upstairs. And if you do this S1 reduction, most part of the S2 just reduced to a interval, and the fixed point you blow up to a circle. So that's going to be like the skeleton downstairs. So I was wondering, maybe in your general construction, this conic vibration, perhaps one can also do a skeleton upstairs and downstairs and match them up.
I am not a skeleton kind of person, so it's
every person has a skeleton. No. I mean, that's a nice idea, because your skeleton is somehow a generator of your apt Fukaya. So your category is endomorphisms. It's modules of endomorphism with skeletons. So if you have it explicitly, then.
I'm not surprised one can try to do that. Of course, one has to understand what S1 equivariance means, but right. So I'm more like a Flirt theory kind of this general approach. And skeletons are of course wonderful things, but they're limited to exact categories, right? So
exactly, yeah.
So exactly. So this is just a general. I think this is these conjectures are sufficiently robust that they can be studied in many different settings. Yeah,
that's great.
More questions?